can follow this procedure. I can do this. Okay. LADEE, Lunar Atmosphere and Dust Environment Explorer. It's the biggest little lunar mission that you probably never heard of over the last year or so. But it was NASA Ames Research Center own little lunar mission. We built that spacecraft to do a specific set of tasks at the moon, which we accomplished basically last winter and spring. And tonight I'll tell you a little bit about it and some of the exciting things that led up to the mission flying around the moon at Christmas and afterwards. But it all began back here in 2008 or so after the head of NASA's headquarters science mission director visited NASA Ames and said, oh, those are the guys I want to fly a little mission with a focused set of objectives. Something that hasn't been studied very much over the years is the composition of the tenuous lunar atmosphere. Some of you are probably saying to yourself right now, atmosphere? The moon has an atmosphere? Yes, it does. We'll get into that in just a second. So we needed to understand it. And at the time, in 2008, the Constellation program was still going on. And humans were going back to the moon. And it was going to be a very busy place with a lot of missions landing. And the environment would be disturbed by all this activity. So we wanted to go back and characterize the pristine lunar atmosphere, all that environment above the moon before humans got there and messed it all up. So that was the objective. And then there was a kind of an existing lore or myth about lunar dust actually lofting off the surface. We wanted to put that to rest or confirm it. And we wanted to do this to demonstrate a low-cost lunar mission, something that would be done cheaply, far less expensively than some of the missions that are flying today. For example, the Mars rover, the Curiosity rover, is about $2.4 billion worth of hardware on the surface of Mars, and this is substantially more than a factor of 10 smaller than that. We wanted to also use a low-cost launch vehicle, and for that, we actually used a repurposed intercontinental ballistic missile. You'll hear more about that in a minute, too. The moon does have an atmosphere. It's a very tenuous atmosphere. You might say that LADEE was much ado about very, very little because the atmosphere is so tenuous and thin. Here in this room, where we're breathing the air, there's about 10 to the 19 molecules per cubic centimeter. That's a lot of molecules in that. But just above the lunar surface, the same volume of space, 1 cubic centimeter, contains only about 100,000 molecules. So it's a better vacuum, actually, than we can achieve here on Earth in the laboratory. And you could actually use telescopes that are set up properly with either coronagraphs and filters to actually image the sodium part of the atmosphere of the moon. One of the constituents is sodium. So if you're set up to do it with your equipment, you could actually image the part of the atmosphere of the moon. The moon's atmosphere is a kind of a thing called the surface boundary exosphere. What does that mean? An exosphere is an atmosphere where the molecules and atoms don't collide with each other. They actually are out of the collisional regime. Their space is too great between them for them to collide. But what they do collide with is the boundary of either the exobase in the terrestrial system, or in the case of the moon and Mercury and a number of other objects out in the solar system, it's actually the surface of the planet itself. So the molecules are actually bouncing off up and down, following ballistic trajectories, and then bouncing off around that, hopping around the surface like bunnies, one journalist described it. The moon isn't static. There's a lot going on all the time. This is an impact that was imaged here on Earth of a meteoroid slamming into the surface, and that impact vaporization, the vaporization of that particle plus some of the lunar material, helps create the atmosphere, and we'll see more about that in a little bit too. But there's a lot of other things that are going on with the moon. Because it doesn't have a thick atmosphere or a strong magnetic field, particles can rain down on the surface of the moon, making it a fairly inhospitable environment, but also liberating atoms and molecules from the surface. To put things in perspective a little bit, again, lunar exosphere is bounded by the lunar surface. You can't go below the lunar surface with atoms and molecules, but you can hop above it. To get a sense of how tenuous that actually is, that corresponds to the same density that you would find not at the International Space Station, but actually well above the International Space Station, where we normally think there isn't any atmosphere. There is, but it's very, very tenuous.
How many miles up?
This is like 380 something. I don't know. I don't follow ISS. Sorry. Oh man, that's being recorded too. Okay, I love the ISS.
I can edit that out.
I'm so glad. There goes my job. Okay, so the moon is one case. It's our nearby case. It's our nearest neighbor. It's easy to get to. It's one place that has a surface boundary exosphere, and the dust process is going on in the surface boundary exosphere. But it's not the only planet in the solar system. It's not the only body in the solar system where this is going on. Mercury definitely has a surface boundary exosphere. We know something about it. It has sodium in its atmosphere, potassium in its atmosphere, calcium in its atmosphere. Weird exotic things like metals are the things that populate these exospheres. The outer planets' moons, many of them have significant surface boundary exospheres derived from their surfaces, derived in the case of Io from volcanoes spewing out material. The larger asteroids also have this kind of exosphere, and Kuiper belt objects. So this is actually the most common form of atmosphere in the entire solar system, just by sheer number. And so the big massive atmospheres like our Earth and Venus and Jupiter and so on are the exception to the rule just by number. Okay, dust. Is the lunar sky dusty? Back in 1968, before the Apollo landings on the surface of the moon, we sent robotic surveyors to the surface of the moon. These are TV pictures from Surveyor 7, which landed in 1968. And after the sun went down and Surveyor was still operating, it looked out toward the sunset to see the sunset. And because there's very little atmosphere there, it's not like the rosy skies that we see. But they did see a glow. And that glow was confined to just above the surface as they could see it in the distance there. And it changed slowly over time. And so the question is, what the heck is that? If there's very little atmosphere here, what does that do to? There isn't enough gas on the surface of the moon to do that. So out of this came this idea that there may be electrostatically levitated dust off the lunar surface that after sunset, the sun is illuminating and the light is forward scattering through that to your eyes or to the TV camera of Surveyor in this case. There were also sketches made by the Apollo astronauts that suggested from orbit that they could see rays of light as if there was... how many of you have watched rosy-fingered dawn or rosy-fingered sunset? You see beams of light coming off over the horizon before the sun comes up in the case of dawn or after the sun goes down. What great! One person there has seen this. Oh, two! Yay! Anyway, you know what I'm talking about. And the same thing sort of seemed to be happening at the moon. And the only way to explain that in a basically tenuous atmosphere situation like that is if there's something up there scattering the light, an aerosol or dust particles or something. Finally, there was a measurement made from the surface that suggested that there was an enhancement in dust falling on this instrument, both at sunrise and at sunset. So this is a lunar month right here. So there's plenty of evidence to suggest that something like this is going on. And one of the reasons for that is that the moon, again, because the atmosphere is so thin, it's exposed directly to ultraviolet light from the sun, extreme ultraviolet light, which can charge things up. And because the atmosphere is thin, that charging remains. It's almost like being in space at ISS, right? So the things that's going on there is governed by the ambient ultraviolet light raining down on it and how much electrons are around in the plasma surrounding it. I'm not going to go into that very much, but if you're interested, we can talk about it later. These are the three sciences.
Is there an electrostatically suspended dust?
That's what we're going to talk about a little bit later. I'm not going to tell you yet. These are the three instruments that we flew on the spacecraft to observe both the dust, if it was there, and the tenuous atmosphere. This is the neutral mass spectrometer. The way it works is it actually inhales, well, it doesn't inhale, it just runs into particles of atoms and molecules from the atmosphere go in and are analyzed for their masses. And so you can separate things like oxygen from nitrogen and argon from neon and helium and so on. And so that's one thing that actually measures in situ what's actually there. And we also flew an ultraviolet invisible spectrometer, which was looking for emissions from the atmosphere. So for instance, like the sodium glow that you would see, it's the same glow as you see in sodium lamps around the city. But it's the emission lines that are distinctive emission lines of gases like sodium and potassium and others, titanium and so forth, that might be there. It's also able to see the scattered light from dust, if dust is there. Finally, we had a lunar dust experiment, which actually is this coffee can shaped thing. Did anybody remember coffee cans in this room? Coffee cans. Now it's like bags of Pete's and stuff, right? So there were coffee cans. And so it's a fairly small object, and the way it works is that door opens right there, and as LADEE is flying along at very, very high speeds, dust particles, if they're lofted off the surface, actually get snapped up by the LDEX as it goes through. And so it was looking for distinct particle impacts from dust that it was slamming into at 3,600 miles per hour or so, which is the orbital speed. We also flew a lunar laser communications demonstration. This was a laser comm system that actually was communicating back and forth between a ground station on the Earth in a couple of different places here in the U.S. And the laser system on board LADEE was transmitting back and forth. And we got up to 622 megabits per second downlink out of this, which means you can actually stream video from deep space like this, which would be cool if you had video to stream from up there, Justin Bieber or something like that.
And that compared to radio connection, what's the difference of the download?
This was much higher downlink than
Yeah.
LADEE used for telemetry.
Right.
So by orders of magnitude.
Mm-hmm.
So and so if you do this, it really opens up the bandwidth, and it's easier to establish a ground station because it can be smaller. And you can see here, these are actually 4 telescopes, and I can't recall what the diameter is, but they get very, very good signal out of that. And you can place them wherever you need to on the Earth. So if the sky is cloudy in one location, you can go to another location that's clear and do the comm. Here's a picture of LADEE as it was kind of naked, getting built. Their reaction control system is in here. All the guts of the thing includes a propulsion system to go into orbit around the moon. 2 of the instruments sit up here on the top deck, and the laser comm system is here in the neutral mass spectrometer is there on the side. So it's about as tall as a tall guy or lady, a tall person, and there's a technician right there. This is LADEE undergoing testing. It's actually going through spin balancing and vibration in that situation, getting prepared for launch. Let me say a word or two about the launch vehicle, because this is kind of interesting. We used a Minotaur 5. The Minotaur 5, this is the very first use of the Minotaur 5. It's comprised of a Peacekeeper intercontinental ballistic missile in the first 3 stages. So this is actually an Air Force weapon, if you will. It's been repurposed for civilian purposes. And so the first 3 stages that light off on this thing are very, very reliable. And then it's on top of that sits another stage 4 Star 48 solid rocket and a Star 37 solid rocket. So we have 5 stages in all, and LADEE sits on top of the entire stack. And so that was a very, very cool thing. And one of the reasons it was very, very cool is that many of you, I'm sure, have been to like shuttle launches or Delta launches, big launch vehicles, and they rise off the pad very stably and everything like this. That's an intercontinental ballistic missile, and it doesn't stick around. It goes. It just like took off, and it was over. It's like, well, why are we standing out here? So it took off, and it was a really cool launch, and the location was unusual too. Wallop's flight facility is actually on eastern Virginia, out near Chincoteague Island, that area where the Horsies are and stuff. As a result of that, actually, folks in D.C., all the politicos in D.C. could actually see the launch, and all up and down the eastern seaboard you could see this launch, and it was seen. The weather was good enough for that. And so this is a site fairly close to the launch. This is what it looks like, a nice, beautiful time-lapse thing. That's first stage separation right there. Off goes LADEE. It was a pleasure to see. And here's a view from the Big Apple.
Wow.
You can see it from up there and even further north and south to North Carolina as well. So that's one of my favorite pictures right there. Of course, if you're really close to the launch, then things get exciting. And this is our launch frog. This is the guy that photobombed our launch. It was not a good day for amphibians. Although it's a suborbital flight, so it wasn't so bad. We took a little while to get to the moon, and one of the reasons for that was because the launch vehicle is a stack of 1, 2, 3, 4, 5 solid rockets, and solid rockets have the behavior of like, you can't turn them off. They go the way they go, and there's nothing much you can do about that. So if there's any error in that burn, or if it burns hot or if it burns cold, you've got 5 uncertainties stacked on top of one another. So we had what's called dispersion, potential for dispersion in the launch, and that means that we could have been launched fast or launched slow when we finally got it injected. So we built into the mission plan 3 separate loops around the Earth, very high loops with apogees of increasing altitude, to take into account any dispersion, any of this launch dispersion, any of the launch errors that would introduce the inability to get to the moon directly. So we were taking care of that. But it turns out that the launch vehicle, this first Minotaur 5, launched us perfectly. So we didn't use very much fuel in this process of getting to the moon. By the time we got out to the moon and carried out the lunar orbit insertion here in October, we had a lot of fuel. We had far more fuel than we expected to have. We went into orbit around the moon initially with a high eccentric orbit, and then very gradually sort of narrowed that down and finally got into our commissioning orbit where we started looking at the instruments. This shows a history of the LADEE mission in terms of the apoapsis altitude, that's the highest point in the orbit above the moon, and the periapsis altitude. Pardon me. Thank you for dinner, by the way, members of the SFAA. It was delicious. Thank you very much. That was awesome. I apologize. So we dropped down to low altitudes because this is where the gas and dust are going to be of greatest density. So we were down below 50 kilometers for the most part at our periapsis altitudes. And later on out here we went even lower. We got brave and brought the spacecraft down to very low altitudes indeed until finally we hit the 0 altitude in April. So a little bit about the science. So one of the things we discovered was, or not discovered, but actually established with much greater detail, was the presence of argon in the atmosphere. It was detected back on Apollo 17, long ago, many years ago. Argon's present there. It's actually something that comes out of the moon as a result of radioactive decay. Potassium-40, which we have here on Earth, in fact all the planets have it, they're born with it. And it decays gradually, has a half-life of 1 billion years or so. And so potassium-40 is decaying all the time in the crust and interior of all the planets. And it leaks, and one of the products that it creates is argon-40. It's a noble gas. It doesn't want to attach to anything. Noble gases are chemically kind of inert. So it leaks out of the interior of the moon, and then once it gets out, it begins hopping around on the surface. And on the day side, it can give a substantial amount of atmosphere. In fact, it's one of the 3 major constituents of the lunar atmosphere. But at night, it gets really cold on the moon. We'll go into this in just a second, but it's really cold. It's 100 kelvins, which is, as you can work it out, it's like minus 173 Celsius. Turn that into Fahrenheit if you like. Anyway, it's really cold. It's colder than Minnesota. It's so cold, in fact, that gas actually adsorbs to the surface of the moon, and only a few of the atoms are actually hopping off. So as a result of that, on the night side, as LADEE flew around, it didn't see much argon. But as soon as it got to dawn, the argon, now exposed to sunlight, would hop off the surface. And I'll show you more about that in a minute, too. But that's one of the important findings. We were able to map out how argon and other gases are distributed around the moon. This shows what we knew from Apollo. They were only able to make measurements on Apollo during the night side. So this is sunset right here, this is sunrise over here. This is the night side of the moon, and this is the density observed from the surface with an instrument on the surface back in 1973. And what we saw is right after sunset, the density of the argon would decrease and decrease and decrease as we approach dawn, and then suddenly jump up actually before sunrise. And why is it going up? Well, they figured out that what's happening is the argon is leaping off the surface on the day side, and some of those atoms are actually hopping back across to the night side. They're blowing like a wind, if you can call this a wind, into the night side. So you actually see a precursor of dawn that way in the data. And with LADEE, we were able to actually take it even further. So we crossed sunrise into the day side. We were able to make measurements throughout the day side. The density maximizes at the sunrise bulge because of that sudden exposure now of frozen or adsorbed argon on the surface now being let go because the surface is warming up. And as it gets warmer and warmer, the gas atoms actually can jump higher and higher in the atmosphere, and the actual local density goes down. And let's see, that's scale. You don't want to talk about scale.
Question.
Yes, sir.
In an earlier slide, there was the phrase thermal desorption. Is
Mhm.
that this?
Yeah.
Thank you.
Yeah. As you warm things up, suppose you had well, actually we'll get there in a second. Another curious thing about the argon is that there's a location on the lunar surface, and some of you will recognize this in a little bit, a location on the lunar surface that likes to have more argon-40 over it. And it's seen at all local times. It's not a local time effect. It's not the dawn effect at all. It's a specific location on in the western Mare. Those of you who are moon aficionados will recognize Okeanos Procolarum over here and Imbrium a little bit to the north. LADEE orbited at fairly low latitudes, and so this is the region where this stuff increases. So there's something special about that part of the moon, and it's not as special elsewhere on the moon. And it turns out that's a location where a lunar prospector many years ago mapped out the concentrations of things like potassium-40, uranium, thorium, radioactive elements. And they tend to be concentrated in these western Mare regions. These are basalts and results of the impact of the Imbrium impact or crash created a huge basin, was then subsequently filled with lavas. But that's where the potassium-40 is coming from, and that's also where you see the peaks in this thing. As a matter of fact, for this time frame, LADEE was flying quite close to Aristarchus, which is an especially hot spot for potassium-40 thorium. The Aristarchus is special, it looks like. Yeah. And people have been talking about lunar transient phenomena in that part of the moon for a long, long time, so that it may not all be just nonsense. It may, in fact, have some basis for a fact there.
What's the scale of the lower picture? How many miles north and south?
It's the polar moon, right?
Of this one?
Yeah,
This is a cylindrical projection, so it's pole to pole.
the total. Okay.
Minus 90 up here, positive 90. So this is longitude and this is latitude from pole to pole. Yeah, I should have put a map of the lunar surface on it to compare. It's also a location where there's more rocks, it turns out. The rock abundance on the lunar surface is controlled by how long the surface has been exposed to micrometeoroid rain. For 4 billion years, if you've got micrometeoroids slamming into you day in, day out, you get worn down, and you actually see fewer rocks on the surface in older places. But the younger places can have more rocks exposed, and in particular the Mare surfaces, which came, the basalt flows that came later, are younger. So there may be a connection with that as well. So we're still studying that. We're still trying to figure that out. Argon wasn't the only thing that the neutral mass spectrometer saw. We also saw neon-20, another noble gas, and helium, regular old helium like you put in balloons and then talk funny after you were neon, we're showing you data from the night side now. So here's sunset over here. Remember we were looking at this for argon earlier. And at sunset you see the density fairly low. As you go through the night, the density increases and increases at LADEE's altitudes. And the reason for this is it's getting colder. After sunset, it's still kind of warm, but it's getting colder and colder and colder. And actually, the neon is kind of like settling closer and closer and closer to LADEE's altitude instead of being really high. So more and more and more of the atoms are actually at LADEE's altitude. After sunrise, everything is warm again. The surface that the neon is in contact with is warmer again, and those guys leap up off the surface. I'll kind of show you a cartoon of that a little bit later. Helium is the lightest of all, except for the hydrogen, and I'm not talking about the hydrogen tonight, but helium is also displaying some of this effect. This is due to the cooling of the night side, but this is also anticipating dawn. Helium, as I'll show you in just a minute, has a longer ballistic hop length than neon. There's a factor of 5 difference in the mass, so just kinematically, they hop to different, at the same temperature, they hop to different lengths, different distances. Both of these constituents apparently come from the solar wind. So they're actually not native lunar gases at all, but they're delivered by the solar wind to the lunar surface. So this is the picture that we ought to have in our head of what happens to a gas atom or a molecule on the lunar surface. Again, this is a surface boundary exosphere These things don't know anything about each other. They only know about the surface that they came from, and once they hit the surface again, what the temperature is at that location. So these guys are hopping off the surface. Once they get into the cold night side, you can see they sort of slow down and hop they hop randomly, but they hop at over smaller hopping lengths because the velocity at which those guys are kicked off of the surface grain is lower. When they happen back onto the day side again, then they hop larger distances. And so this explains an awful lot of what we see in the lunar exosphere. This isn't a real good analogy, but the Eskimo trampoline effect is the following. If you put a little kid on the Eskimo trampoline, and you didn't care about him for give it the same amount of energy on the trampoline, everybody in the village, doing this, the little kid's going to go a lot higher with a lot more speed than, the fatso in the village or something. They're not going to go as high. So that's kind of an intuitive way of looking at what's going on the lunar surface and atmosphere. And so things like helium, the Eskimo trampoline effect is going to send helium on average to higher altitudes, neon to intermediate altitudes as it hops around, and argon-40 being even more massive still is going to go to even lower altitudes still. So that's why these things are distributed in the exosphere differently with height.
I'm having trouble getting my head around something. I would assume a lot of molecules hop around from warm surface. And I guess the issue is, what is the definition? What is the minimal amount of activity you need to call something an atmosphere? Because I would imagine you have a piece of equipment that's measuring a discrete thing, but I imagine on Earth you have this sort of bouncing around of molecules when it's hot also. How do you define what is an atmosphere?
Well, this is an atmosphere, that's for sure. Right?
Yeah.
What we're living in right here.
Density or a minimum number of particles?
This, you could think of an atmosphere as actually no, it doesn't. There is no minimum, because what you're talking about in these cases is a transition from densities of rock, or powdered rock in the case of the moon and Mercury and so forth, to something very tenuous. But no matter where you go in the solar system, there's always going to be vapor out there of some kind. So as long as it's a body, and as long as it's got some amount of gravity, and as long as there's a vapor coming off of it, or something being delivered that turns into vapor, that's going to be an atmosphere.
You're really measuring not an atmosphere, you're really measuring extension of molecules above the surface of the body. Kind of.
You can call it whatever you like, it's still the same thing. Yeah, that's true. Go ahead.
Is it fair to call it lunar weather?
Depends on what you mean by weather. Now we got something else to define. Because the molecules are hopping independently of one another, they're not really organized enough to do anything like make clouds or anything like that, right? So we're talking about much higher densities here on Earth and the other major planets. That's what makes these things really special, because they don't resemble what we have here in this room at all, in the way they behave.
So I'll add to that. So there's no fluid dynamics that are happening. This is not acting like a fluid. It's acting like a bunch of molecules that are independent.
Yeah, it's not a fluid. Right, definitely not a fluid.
Yeah.
But they are held to the moon by gravity, right? I mean,
Some of them are, and I'll get to that in a minute too. Actually, it turns out that helium is not. Helium on the night side is bound, and the ballistic trajectories that helium makes on the night side, because it's cold enough, the bulk of the population is below escape velocity. But once it gets to the day side, where the surface temperatures are high, then the energy delivered to those helium atoms actually is higher on average. And some fraction of the population of helium are going to be very, very high speed. And they end up going above the escape velocity, and they are lost. That's the main loss mechanism for helium at the moon. So here's the moon. It's hot. It's hot on the day side. It's cold on the day side. Places that have a lot of rocks happen to, like Taco down here, stay warmer through the night. Rocks stay warmer. You can see that in the desert if you go out into the desert. You can see that the soils and stuff cool off very quickly, but big rocks will stay warm. So since there's a huge range of temperatures on the moon between day side and night side, 112°C is about as hot as it gets at the equator, and minus 180°C on the night side, gases that can condense on the cold surface at 100 kelvins or so will freeze out, and that includes argon-40, but not just argon-40. gases that do not actually get distributed in the atmosphere according to the surface temperature. And the density that you measure anywhere on the surface or at LADEE's altitude will depend on the temperature. It will be smaller when the temperature is higher, and it will be greater when the temperature is lower, just because these atoms are, in effect, settling down over cold bodies.
And that animation is only the Earth-facing side of the moon?
Yeah, but
Cool.
the backside looks similar. It's hot there, too. Okay, I'm going to run this little animation for you guys. What I'm trying to show you here, and I need to pick up the pace a little bit, but I'm trying to show you argon-40 and how it would behave if you turn on canned heat down here and warm things up, much like what happens to the lunar surface after you go across the sunrise terminator. So let me try and turn this on. Can't see my mouse. There we go. So watch what happens. I'm going to turn on the heat here. These guys are just kind of sitting on the surface. A few of them are hopping up, but not many. So mostly it's a matter of being condensed. Now the temperature is going up. These are in kelvins, so it's still kind of cold. But it doesn't go about above 170 or so. These guys pretty much desorb completely from the surface, but they are still concentrated toward the surface. And on the moon, of course, there's no lid on this thing. In fact, they'd be hopping to great distances. And the hotter you make it, the further they go. The hotter you make it, the higher they go. And the more those atoms are actually distributed over a much, much larger altitude range. And therefore, the density of where you are is lower. So I hope that makes sense. I'm going to show you neon now. Neon, oops. That wasn't what I intended to do at all. Anyway, neon doesn't do that. I have lost control of my presentation.
If you look on the screen, you can see it on the screen.
All right. Little cooperate. This diagram is meant to show what happens, where helium comes from. And I'm showing you two lines here. One is a red line, and one is a black data points that come from the LADEE measurements. And this is basically the complete mission flowing along here. And what I want to point out is that the solar wind is delivering virtually all the helium that the moon has. And we see great excursions in solar wind helium being delivered to the moon. And it turns out that the lunar atmosphere just follows that very, very closely like a dog. And just it rises when the helium, doubly charged helium in the solar wind arrives, drops when it goes down, and so forth. So we now know, we didn't know before, but we now know that solar wind is driving both neon and helium, and for helium in particular, it goes up and down just with the solar wind. So that's kind of cool. And I don't know why I can't do this. I've done something to my machine. Okay, we also observe sodium in the exosphere of the moon, and it turns out to do kind of interesting things. Sodium actually will increase and decrease with a couple of different effects. One thing is meteor showers or meteoroid streams, the same ones that produce meteor showers here on Earth, the Geminids, the Leonids, and so forth, also produce sodium on the moon. So you'll see enhancements in the sodium exosphere, this metal, this alkaline metal, actually increases after meteor showers, but it also changes in association with crossings through what's called the terrestrial magnetotail, or the geomagnetic tail. Out here, for most of the month, the moon is in its orbit, is in the solar wind. It's exposed to the solar wind in a process called sputtering. Solar wind ions are coming in from the sun at high energy, and they impact the surface, and these little ions drill into several hundred angstroms of material, and actually they deposit so much energy they actually eject some of the ambient lunar material, and that gives an explanation for where the sodium is coming from. But micrometeoroids are also delivering sodium apparently to the lunar surface, and so that becomes a vapor that then settles in and actually can settle out on the night side as well. And just to show that maybe a little bit more clearly, these blue areas here are full moons, and that means that the moon is in the geomagnetic tail and therefore protected from the solar wind. When that happens, the sodium kind of goes away. But as soon as the moon leaves the geomagnetic tail and leaves the protection of the geomagnetic magnetic tail, the sodium comes racing back into the exosphere again. In fact, it comes back even stronger than it was before, and then settles down again as the months go by. So each of these is a lunar day, and each of these is a magnetic crossing. We see the same behavior month after month. And not just sodium, but we also see potassium as well. It doesn't behave quite the same way as the sodium does, but again, there's a monthly cycle, and we don't understand it. We don't understand why it does things that are different from sodium, and that's one of the things that's ongoing. So the bottom line for the exosphere, if you count everything up, if you're an accountant looking at how much of each thing is in the lunar exosphere, it's dominated by helium. Helium is coming from the solar wind, and that goes up and down according to the solar wind, just like I showed you. The second most important constituent is an isotope of neon called neon 20. There's also neon 22 out there, but it's far less abundant. And then the third most important is argon 40, and that's coming from the interior. So you've got two solar wind delivered products, as well as argon coming from the interior. And then stuff that's left over. A very small slice of the pie here, and that consists of a bunch of different things at much, much lower abundances. Things like aluminum, a metal. We have seen water, sodium, hydroxyl, OH, oxygen, magnesium, potassium, but they make up a very small fraction of the lunar atmosphere. Let's talk about dust. LADEE flew around the moon and made measurements of the dust density as a function of the altitude. Altitude is shown here kind of radially going from the center of the moon. This is our commissioning orbit. This is 250 kilometers, so this is where we made our initial measurements. But down here, you should get the sense that the dust density seems to increase closer to the surface of the moon, but it also has a vertical time distribution that actually is maximized over here at the sunrise terminator. Who can tell me why? Anybody got any ideas why dust would be higher on that part of the moon? That's the part of the moon that's moving in its orbit around the sun. What's going to ram into that? Anybody got a clue? What?
Solar wind.
No? Well, solar wind is actually coming in on the day side. It's coming from the sun.
Oh, that's the direction it's traveling around the sun?
Yes.
So it's the interstellar space there?
It's the micrometeoroids that you see
Right.
after midnight here on the Earth. They're meteors, right? Meteors that you see in the sky. If you look for them at 9 p.m. or something like that, you're going to be disappointed because the flux is very low, right? But if you wait until 3 a.m., you have to manage that. Then you're going to see far higher flux, especially with showers that are coming from that direction. So that's the fundamental explanation for why this side of the moon has more dust. Why does it see more dust? Well, the moon is a gigantic witness plate for all the micrometeoroids raining down on it. So each of those micrometeoroids is coming in at 20 kilometers a second or something like that. And that's really fast and that's really energetic. And so when it hits the lunar surface, bam, right? It's got each of those little guys hitting is an explosion. And it sends all kinds of ejecta, like an explosion, up into the exosphere to very high altitudes. And so each of those is raining down, creating this basic asymmetry to the dust. So it's really not dust, it's not levitated dust, it's just gravitationally launched dust that comes from all these little explosions all over that upstream side. So it's like when you're driving through rain or when you're driving through Iowa or something in the summer when there's bugs, bugs are hitting the windshield, right? They're not hitting your back. They're not hitting the back window. They're hitting the front because, like the moon, you're traveling, through these bugs. I probably could have found a better simile. This is the altitude distribution of the dust density. So it turns out that it falls off at high altitudes, pretty much like you would expect, like exploded dust to do. And then as you come down closer to the surface, it just kind of trails off. And this is pretty much in agreement with what you would expect for ejecta from all these little craters that are being formed by micrometeoroids. And I won't spend too much time on this. This just shows the same thing, that in fact, that as you come down in altitude, the number of densities increase up to a point. This is kind of a fun little movie because it shows visually what I'm talking about here. So imagine that, a dust particle impacts here, or even better, a golf ball sized meteoroid smacks into the lunar surface and throws up a whole bunch of different dust, ejecta, primarily stuff from the lunar surface. And imagine then LADEE flying through there, in this case at 100 kilometers or something like that, flying through this. And it turns out that we were close to these explosions on occasion. Let me just run that one more time because it's kind of fun. So you can imagine coming along here and not seeing much of anything and then smacking into this flak cloud of exploding ejecta. And we actually saw that every now and then. We also looked for dust with our star trackers. These are imagers. They're deliberately defocused imagers because they're star trackers. They're looking for the constellations in the sky so they know then how LADEE is oriented. So this was for our attitude control system. But we took pictures as we flew around toward orbital sunrise. So the sun is over here, and we're coming around. We're looking for dust that's illuminated by sunlight coming from the other side. And you may think that that's what this is, but in fact, this is actually zodiacal light as imaged by these star trackers. And you really don't see anything apart from zodiacal light and the corona of the sun. So that tells you right away that whatever the Apollo astronauts were reporting, probably, it was either happening then and not happening now. We just don't see any evidence for it. So this levitated dust thing doesn't seem to be there. However, you can see kind of the terrain being lit by secondary reflected light from features that are sunlit just at the horizon. This is a movie of a series of star tracker images. So this is orbital sunrise as seen by LADEE. We took these pictures just in order to try to look at this dust question, but it's cool to take home movies with a spacecraft that really had no dedicated imagers. Well, all good things come to an end, and hopefully this talk, right? So, including the impact of LADEE in April of 2014. We brought down the spacecraft to very low altitudes on a couple of occasions just so we could make measurements way, way down close to the lunar surface. Just a few kilometers off the lunar surface. And on April 18th, we smacked into the side of Sun V crater. This is the crater that's just over the far side on the, is that the eastern line? I can't remember. Anyway, it's west longitude, just beyond. So we smacked into that, and that was the end of the LADEE mission. And that's what our trajectory looked like leading up to that. It's kind of a high point we did not get over. And I have to, I can't resist, I have to do this. I have to show you something else too.
That wasn't on purpose?
Yeah, it was. Actually, we deliberately dropped to low altitudes. And we knew we were going to smack on one of the orbits on that day. And it wasn't entirely clear which one. Let me show this video.
Do they let you crash on the moon, or maybe the environmentalists have some objections?
They do let you crash on the moon. It's a good thing. So there's the Earth. We were talking to LADEE at the time. We had comm coming down from LADEE. There's the Pleiades right there, sort of put you in perspective. We are traveling just a few kilometers above the surface of the moon, minding our own business, saving data, another orbit for LADEE.
Wow.
And like I said, all good things come to an end. And this is...
Was there any signs coming out of the collision?
Yes.
Okay.
After the fact.
Yeah.
So, turns out we made a crater, as you might expect. We're traveling at 3,800 miles per hour, something like that. So, you slam into a bridge abutment at 3,800 miles per hour, something, it's not going to be a good day for you. So we smacked down, we created a set of ejecta here. This is a ratio of two images from Mark Robinson of the LROC. You guys may know about LROC. It's the imager aboard the LRO spacecraft. So they took a picture of our before and after. They ratioed them, and so this is the lightening and darkening of the lunar surface as a result of LADEE impact. We put right there a crater, about 10 meters across, pretty much as expected. So it kind of confirmed models of low speed grazing impacts like we had. So it's a good fiducial mark for the science of impacts.
Did you see you made the dark spots too in that picture?
I believe so. I don't think those are, well, these maybe not. The problem is that the images were taken at two different times with two slightly different lighting conditions. So when you ratio them, you're going to end up with a few artifacts. That's the problem now. So let me get out of this presentation.
When you're flying real low like that, do anomalies in the density of the moon make the orbit go crazy?
Yeah, we were battling that for the entire mission. It's a study in the gravity field of the moon to fly a mission like this at low altitudes, especially in retrograde orbit. So it's the mass cons on the lunar surface, in the lunar subsurface actually cause a lot of perturbations. And so for part of the month, your orbit will move off more elliptically in one way, and then the other half of the month it'll move the other way, and eventually these perturbations build up to the point where you can't stay in orbit, you just smack into the surface sun. So it's inevitable. Unless you have a way of getting out of orbit again, you're going to smack into the lunar surface. All right, so this is just a wrap up. We've made argon, neon, helium in the exosphere. We know they're there. We understand how they vary. We have good models for how they hop around on the surface. There are many other interesting species that are currently being studied, including, we think, water. And this is important. Water is important on the moon because there's seemingly very little of it, but what there is of it is sequestered at the poles in the cold traps. Cold traps at the lunar poles result from the fact that you've got craters on the moon, and there are places where the sun doesn't shine ever, and those places get very, very, very cold. So any atom or molecule going into those locations is stuck for a very long time. And so that's a natural sort of landfill or repository for anything that comes in and ends up in those places. It's going to stay there, kind of a trash heap for the moon. But gold for us if we ever go back there and we can recover the ice. The L-Cross mission, which was an impact mission, crashed into the lunar south pole in one of these permanently shadowed, very, very cold areas, and saw in the plume of ejecta that came up the presence of water. So we think there's a plenty of it there. Sodium, potassium, many other metals probably in the atmosphere of the moon. We're identifying them now. There is this dust cloud perpetually engulfing the moon, and it's sustained by the continual bombardment of the moon by the interplanetary dust particles. And when we fly through streams, that goes up, and it has an influence on the exosphere. You see the sodium go up. But we didn't see any evidence of electrostatically, magically levitated dust hanging out over the terminator. And that, in a nutshell, is LADEE, which is like the last 5 years of my life.
Did LADEE observe the moon during any lunar eclipses?
Yeah.
And follow-up question, if you were asked to design the next probe of the moon, what would you want to have on it?
You're a plant, aren't you? Yeah. Here's the thing about eclipses. The sun goes away. And if you're solar powered, it means you have to dip into your battery reserves. And if you dip into your battery reserves, you get to a point in your, if you're running normally, you get to a point where you reach discharge in the battery, where the engineers come over and, give you a wedgie or something like that. Don't do that. You can't do that. The engineers control everything. So we actually operated up to the eclipse, but not through the eclipse. We couldn't operate through it because LADEE, in fact, was never designed to survive an eclipse. We were prepared to have the spacecraft fail in that eclipse. It was like April 5th. You guys remember when that lunar eclipse was? April 15th? Something like that. Yeah, tax day. It was a tax day eclipse. And so, we power shed. We brought the spacecraft down into safe mode and had very, very minimal number of subsystems operating. We came through it basically fine. There were just a couple of things that failed through the eclipse. So we continued to operate, and it was great. Go ahead.
Are you going to salvage any parts from the mission, or is it just completely left
You mean, did anything come back?
Yeah, pretty much.
Well, it was in orbit around the moon. We never left orbit. We crashed into the lunar surface. So whatever is there is kind of, like in that picture, sort of strewn across the surface. So if you're an entrepreneur and you go land on the moon, you get to recover pieces of LADEE and sell them on eBay. Your tax dollars.
How much did the mission cost?
It was a $280 million mission, including the cost of the launch vehicle, which is usually not included in those things. But that was also a cheaper launch vehicle. So we're actually the spacecraft and mission operations and the science was all less than $200 million.
The Outcross mission extrapolated back to try and calculate how much water was in the South Lunar Pole. I don't know what parts of the moon the LADEE mission covered in its orbit, or whether it even went over the South Lunar Pole. I think it was probably a equatorial orbit.
It was very Apollo-like. It was a retrograde near equatorial orbit. So we
you didn't sample any of the poles.
But we're sampling atoms and molecules that hop around on the surface, and some fraction of those end up just randomly finding themselves in the cold traps at the poles. So the measurements we make of things like water, for instance, or hydroxyl OH, are very, very relevant to one conveyor belt of those particles to the poles for sequestration. It's one way to do it.
Okay.
So the measurements we make and how we end up getting published with peer review and everything like that are going to inform that one avenue of sending molecules into the cold traps to be trapped forever and maybe build up.
So it's kind of a circulation going from equatorial regions towards the poles.
But not coming out. I mean, generally not coming out unless
not coming out of the poles.
Yeah, because it's a cold trap.
Right, it's a cold trap, right. Okay.
So at the beginning of your slides, you showed all the different bodies, and Mercury was there too, and you talked about atmosphere. And to me, it just seems incredulous that Mercury, being a third of the distance from the sun as we are, with that kind of solar wind, how could there actually be an atmosphere there? Has there actually been evidence that there is atmosphere?
Like I said, they've seen sodium, and they've seen potassium, and they've seen calcium. I believe they've seen magnesium now.
Is that was the orbiter?
They've seen helium. Actually, Mariner 10 saw helium.
Okay.
Oxygen was also seen.
Wow.
So,
that's for the
but
messenger
again,
mission,
these are
right?
the sodium, potassium, and calcium, magnesium we're seeing in messenger. They're still observing it. They're characterizing how it changes and stuff. But it's like anything you can imagine. Even Mercury at perihelion, hotter than blazes on the day side. Anytime you warm up something in a vacuum, it has a vapor pressure, right?
Yeah.
So a rock will have a vapor pressure, and so that's where some of this stuff actually comes from. But not only that, it's micrometeoroids smacking into the surface, creating vapor. Sputtering is going on and creating secondary particles that turn into the atmosphere. Sputtering is like I described, when energetic ions or atoms come in and actually excavate material out of the top. And so as that source, the interior is also venting argon-40 on Mercury, I'm sure. The same
I
as
just think the solar wind would be so strong there.
Well, Mercury has an intrinsic magnetic field that helps stand that off.
Okay.
It's like the Earth in that way. Earth's dynamo is much more active and bigger.
Yeah.
So the terrestrial magnetic field actually extends out quite a ways. So like 10 Earth radii or so is where the dayside magnetopause is. And the solar wind sees that, creates a shock wave around, and gets deflected primarily around the magnetosphere. The same is true at Mercury, except for times when the solar wind is very, 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 very strong. And it does happen. So at perihelion, on a bad day when the solar wind has got a high density, it actually pushes that magnetic field down to the surface, and it'll interact with the surface. So it's not completely protected, but most of the time it is.
You said the laser communication systems they were only stationed on in the U.S. So
Yeah.
you were out of contact with on the other side of
For the laser comm system, yes, but for radio transmissions, our operational way of getting commands up to the spacecraft and telemetry back from the spacecraft, that was handled by DSN, the Deep Space Network. That's the normal radio approach. So we had the three big dishes around the globe in Madrid, Spain, at Canberra, Australia, and at Goldstone. So we had the moon covered virtually 24/7. So we didn't have any problem with that. The LaserCom was a demo, and so we couldn't rely on a technology demonstration for our communications. NASA didn't allow us to do that. So it could have been, but since I didn't know if it was going to work or not. In fact, my money was on it wasn't going to work, and I was delighted that it did. And it worked really well. I was really kind of blown away. So it
lost money.
Huh?
You lost some money.
Yeah, betting.
I think I was out of 6-pack. They were nice. They were kind to me. I was out of 6-pack. Any other questions? Yeah.
When the spacecraft was orbiting the moon, did it experience any kind of like atmospheric drag? Did it have to compensate for that, or is it pretty much?
No, because it's so tenuous, it just doesn't have anything like the influence. The thing that's we accounted for the weird lumpy gravity field of the moon. We accounted for solar radiation pressure. What else did we account for? Potential venting from the spacecraft that might influence the trajectory a little bit.
So those were all bigger
that's
factors
it.
than...
Yeah, far bigger, far bigger. I mean, it's really not very many molecules or atoms to run into. So no drag to speak of there. Now, interestingly enough, I pointed out that it was like the terrestrial exosphere above the ISS. The ISS does have to worry about drag because it's actually substantially low enough so that it does see drag, and they do have to boost it every now and then. I love the ISS.
First, this glows in the moon. Glows. This moon glows in the dark.
Oh, right.
Here is something that LADEE doesn't like. And our many, many thanks for this fine presentation.
Oh, thank you very much. Thank you. Thank you.